Welcome to qnawire.
Alright, let's go ahead and solve this problem. So there's a complex looking flux integral that we want to evaluate. F is given as sine of xyz. X squared y squared is the j vector, and the k vector is z squared e to the x over 5. We want to evaluate through the surface 4y squared plus x squared. That's not x squared, that's actually a z squared. My bad. Over the interval x between -2 and 2. Okay, so that should be a 4 as well. Dividing both sides by 4, we will get y squared over 1 squared plus z squared over 2 squared is equal to 1. And if you recall, this is an equation of an ellipse. So I can draw this in 3 dimensions. Not 3, let's call that x. I'm going to make this coordinate y, this my z. You see that in the y direction you go 1 unit front and back, so 1 to -1. In the z direction we go 2 units front and back, -2 to 2. And for x, we know that it goes from -2 to 2. So those are going to be the ultimate height of the cylinder. And the cylinder will have a shape of an ellipse. So I'm just doing the best that I can to make it look nice. May not be the best drawing, but hopefully you get the idea of what I'm trying to do here. We just want to figure out the flux integral with this being the normal vector. And as you can see, it is not a very straightforward normal vector. So we need to parameterize the surface and then figure out what f dot n is going to be, as usual whenever we do flux integrals. So this is a case where the parameterization works out very nicely when we use cylindrical coordinate systems. So this is my choice. X, it just goes from -2 to 2, so x is x. Y here. Y squared over 1 squared, I would like that to be my cosine because if I let z over 2 be sine, x squared plus y squared equals to 1, and things are going to work out very nicely. So z itself is going to be 2 sine of theta, and this will be my choice of the parameterization. So r is going to be the vector x cosine theta sine 2 sine theta. R sub x would be 1, 0, 0. R sub theta, we take the derivative with respect to theta, so it'll be 0, negative, negative sine, 2 cosine, and the normal vector, we can calculate that it will be 0, 2 cosine, sine. Now, f is going to be a very ugly expression, but because I have this to be 0, sine of xyz, I'm just going to leave it as that because I don't really need to write it all out. So sine of xyz, which I don't care much about, x squared y squared will simply be x squared cosine theta z squared e to the x over 5 will be 4 sine squared theta e to the x over 5. So the dot product f dot n will end up being 0, like I said, plus 2x squared cosine squared plus 4 sine cubed e to the x over 5. Now moving on to the integration. The value of theta changes from 0 to 2 pi because we're using the entire angle, one entire revolution, 0 to 2 pi, and x changes from negative 2 to 2, and that would be good enough. That's why the cylindrical coordinate system really works out well in this case. And we're just evaluating 2x squared cosine squared theta plus 4 sine cubed e to the x over 5 dx d theta. Now, if you've done enough of these problems, by now you should realize that whenever you get these kind of expressions, it will always end up being 0. And the reason is sine cubed theta is an odd function. And then we know that we're integrating through the entire revolution. So because of that, we know that the red part that I just marked, it is just going to equal to 0. So what's going to happen here is that in essence, what we're just really trying to evaluate is the integration of 0 to 2 pi, negative 2 to 2, of 2x squared cosine squared theta dx d theta, and I've already given you tips on how to evaluate these expressions. We simply use the double angle formula. Or was it the half angle formula? It's a double angle, a half angle formula. When it's squared, it looks like this, so we can evaluate it. So this is quite a simple integration, so I'm not going to go through the entire calculation, but you will end up having 32 pi over 3. And that's how you integrate this integral.